thank you very much for that introduction. Wow. All these engineers, that's wonderful. I assume a lot of you are engineers. How many are engineers? Oh, that's wonderful. That's wonderful. Well, yeah, good afternoon. 47 years. I've been a revolutionist for 47 years with this stealthy revolution. And GPS is indeed a stealthy revolution, and I thank you for the opportunity to talk about it. And I've been asked to give a little of the history, so I'll do that. And then talk about contributions to humanity. Of course, the engine that's driven it is really engineering. So engines, engineer, and double E, computer science, certainly were at the heart of it, but all disciplines of engineering were involved. And we've continued to call it a stealthy revolution. And we call it stealthy because knowledge of where you are is not, everyone takes it for granted now, but the truth is, many years ago, they didn't have any knowledge of that, and the people who are using it, by and large, have no idea how it works, and they don't have to. Who cares? They just pull out their cell phone, and right away they know where they are. And it's a revolution because I know it's inconceivable to some of you younger people, but 50 years ago, ships got lost in the fog, and airplanes had trouble landing, and people didn't instantly know the next turn. So the revolution has been very challenging. And some time ago, a famous European commented on introducing new things, and this is what he said. It ought to be remembered there's nothing more difficult to take in hand, more perilous in its success than to take the lead in the introduction of a new order of things. Because the innovator has for enemies all those who have done well under the old conditions and only lukewarm defenders, and those who may do well under the new. This coolness arises partly from the fear of the opponents and partly from the incredulity of people, the inability to accept things, who do not readily believe in new things until they've had long experience with them. And perhaps some of you recognize this quote. It's not exactly new. It was stated 7 years ago by Machiavelli. And the efforts to develop GPS were indeed both difficult and perilous, but they weren't unique. And I suspect that many of you are working on products and are perhaps encountering similar resistances. If you're not, wait, it'll happen, because that's the way the world is. But our revolution continues. Let me give you a few definitions. For this group, it's probably superfluous, but I'm going to do it anyway. GPTS, the Global Positioning and Timing Service. I'm emphasizing service, not the satellites with that abbreviation. GNSS, everyone knows. GPS, the other three worldwide systems. Galileo, GLONASS, BeiDou. And then, of course, the augmentations, WAAS, FAA's WAAS is perhaps the grandfather of those. And then PNT, Position, Navigation, and Time. And I'll use those. And again, I suspect you already knew all of those. So my remarks today, I've been asked to talk a little bit about the ancient history. I will do that. Success from failure is what I call it. GPS and GNSS for humanity. I'll touch on some surprises and a little bit on the economic benefits. Don't have a lot of time. Then for the future, I'm going to remind you of the new signals and opportunities, and then I'll have three subjects: a challenge, an opportunity, and a threat. And I'll explore those just a little bit, and then I'll conclude with why is GNSS now ubiquitous? I hope that I won't ramble on to the point that we can't have some questions, because that's always the most interesting part for me. The origins of GPS really began in the early 60s. This was due to the energy and efforts of this man, Dr. Ivan Getting, who was the president of the Aerospace Corporation. He felt there ought to be a better way to navigate using space satellites. He didn't choose a specific design, but at his urging, the Air Force 621B program, a study program, commissioned this comprehensive study that you see here. And this study was revolutionary. These two system engineers did it, Jim Woodford and Hiroishi Nakamura at the Aerospace Corporation, and they discovered 12 ways you could navigate from space. That was over 50 years ago and predated any claims by the Navy that they had invented GPS, by the way. This covered their system and 11 other kinds of ways to do it. And as we will see, we ended up selecting the hardest way. At the time, well, it was the most capable. And at the time, this was classified secret and not declassified until 79, 6 years after we had defined GPS. So by and large, the world didn't know where we had gotten some of these ideas. This was a big help, but not the only one. So I was in LA, at LA Air Force Station on a program called A-Breeze. And in essence, I had a free hand. They gave me $100 million. $100 million. That was when it was worth a lot. And I could spend it any way I wanted. And I was spending it on reentry vehicles. And I was aware of a small study program called 621B, which we just mentioned. They had unsuccessfully tried to start a new satellite-based navigation program. Now, this little small program only had about 2% of my budget. But what happened next, in November, the head of all, let me show you his picture. The head of all space and missiles for the Department of Defense, this gentleman, Lieutenant General Ken Schultz, called me into his office and asked if I would like to move over to 621B, this failing program. And my background was a pretty good match. I had practical navigation at the Naval Academy, and I'd studied inertial and digital under Doc Draper at MIT, and I had led tests and analysis of inertial navigation for the whole Air Force at one point. I taught space mechanics at the Air Force Academy and astronautics for astronauts at the test pilot school, but I was very leery. And I asked him, I'll volunteer if I can lead. He would not promise that. But on the other hand, he didn't not promise it. But being a general, what he did was instantly transfer me. And so about 2 hours later, I was on the new program. Unfortunately, it was also in LA. The second event, though, that happened, also important, there was a certain Dr. Curry. And Dr. Curry was in charge of all of the R&D money for the whole Department of Defense. And he was down in LA, and so General Schultz was trying to entertain him and said, well, I know how to occupy about 3 hours, send him down to Parkinson, he talks a lot. And so I'm suddenly in this little office, I'm a brand new Air Force colonel, and he is a godlike figure, for 2.5 to 3 hours with a stack of viewgraphs. And he had a PhD, by the way, in engineering, I think. And we had a lively discussion. And at the end of that discussion, something magic happened. Here he is. He's still alive, by the way. Good guy. He became the godfather. He became the champion of our program. And he protected us because the Air Force didn't want it. They did not want what we were trying to do. And a direct informal line of conversation began between the two of us. And I call him the godfather because if anything was going wrong, he would try to fix it for us. And I hope all of you have mentors. You need them, believe me. And I had this fine gentleman. Well, I had some reservations. I'd inherited a design in August of '73, but I decided, well, we're just asking for a demonstration. I went to the big Pentagon meeting to gain approval, and that's what happened. I failed. I did not gain approval. And the GPS Godfather, Dr. Curry, was chairing the meeting, but he called me into his office, encouraged me, says, go back, redesign it now and get it right, and bring it back, and I think we'll approve it. So our program was in LA, but I was concerned that the people in my office were so entrenched with what we had done that I wanted to get away from anyone I thought was going to cast aspersions on new, perhaps far out ideas. So I called that meeting to modify the proposal, and I called it in this building, which it turns out was about 3,000 miles away. And it was by invitation only from me, and I'd already hired about a dozen really superb Air Force officer engineers. These were people with PhDs and master's degrees from MIT, Stanford, Purdue, Michigan, some of the better names of schools that were around. And we spent Labor Day weekend in the darkened halls of this building coming up with a new proposal, about 3 days. Here are some of my heroes. Steve Gilbert was my deputy. Gaylord Green, who was still at Stanford, and some of you may know after he retired from the Air Force, he came to Stanford, and Mel Birnbaum. These are names, if you were in the early days, you would know who these people are. But they were prime contributors, and we put together a proposal, and I'd like to summarize what those fundamental innovations were. They're not going to seem all that fundamental to you because, although revolutionary at the time, perhaps not so revolutionary after you've been using them for 47 years. But the first was the concept. If I can get this to. And we picked the 4-range concept, number 12, of the Woodford Nakamura study. And what that did is gave us passive, one-way, 4-dimensional user position. And it was, as a consequence of being passive, it could have an infinite number of users. There were a lot of other techniques that used 2-way ranging and things. That would not have worked. You would have saturated it with 2 billion users. But we have that advantage. And the user could calculate his own position and only required a simple crystal clock. He didn't require an atomic oscillator or anything like that. And if successful, it would give about 10 meters of accuracy and provide about 30 nanoseconds of timing, probably. Of course, we've gotten better since then, but that was our claim. The second innovation was something called CDMA. And again, for everyone in this room, CDMA, ho-hum, we know all about that. Not then. It was primarily used as a clandestine radio link because it sends out power that's spread across frequencies such that it's only 1% of the natural noise. There was a lot of skepticism about this. And the reason was, how on earth are you receiving this signal when we know it's not even above the natural noise? We'd already demonstrated that, though, and we felt quite confident we could do it. And of course, now you routinely do it with a cell phone. And as a matter of fact, because all those signals are on the same frequency, this is not trivial. It means that the inner frequency biases are locked as soon as you sample that. And it means that right down to the picosecond, you have it locked together. And inter satellite bias is not a part of your problem in accuracy. And as a consequence, that's how the surveyors, that is an underlying reason surveyors can survey down to a millimeter. And the last thing was space-hardened atomic clocks. Clocks had been around. They'd been in the laboratories. No one, the Naval Research Laboratory had tried to fly one, and it instantly got destroyed because of the radiation in space. We were planning to put this in the upper Van Allen belt and to calibrate you. If you were not protected by radiation shielding, 1 minute exposure would kill you. This is pretty hot stuff up there, and we had to design electronics, and I'm pleased to say, looking ahead, we have some clocks that have lasted 25 years in that radiation bath, which is, to me, real engineering. So what happened next? Well, I took the concept and went back and forth to Washington for the next 3 months and finally got approval in December of '73. We said for $150 million, we will develop 6 satellites, a launch system, 9 kinds of user receivers, a ground control system, and an extensive test program. It was one heck of a bargain. Now, true confessions, we overran it by about 15%, but I would contend, nonetheless, that ain't bad. I thought we were doing okay. Now, there's another myth that I'd like to put to bed. They say in Europe, well, it's a military system, and then they later let the civil use it. Not true. Before we launched the first satellite, I told Congress, I testified and said, we are going to have a civil signal that's available, not guaranteed, and it'll be available from the get-go, and I am publishing how you use it. And then everyone asked me, how did you make that decision? I just made it. I didn't ask anyone. If I'd asked anyone, there would have been a lot of people trying to tell me no. So instead, I said, no, this is the way it's going to be. And no one, of course, most people thought the whole thing was going to fail anyway, so probably pretty easy for them to say that. Very proud of this. First launch, 44 months after we gave a contract go ahead. Today, it's taken us more like 8 or 10 years to do these kinds of things. Never built such a satellite before. And then a proof of the civil capability. The first civil set that locked on GPS, to my knowledge, was built by students in England at the University of Leeds under Professor Peter Daly, which says that we had indeed sent out a spec that allowed a user to completely define and navigate and use this system, again, without any guarantees, but nonetheless, there it was. So we did extensive tests in '78. We proved, at least to my satisfaction, and anyone else that I think was open-minded, that we met all the global objectives. Unfortunately, the Air Force still didn't want to do this, even after the testing. They didn't want to fund it. They'd rather buy more airplanes or something else. But the trouble was, if the Air Force had been left to their own devices at that point, the program would have died. It would have died because of lack of budget. But the civilian leadership in the Pentagon intervened and, in essence, forced the Air Force, Dr. Curry did, as a matter of fact, forced the Air Force to fund it. And finally, we got full operational capability in 1995. We could have had it at least 15 years earlier, but the go slow on the budget precluded that. But then along the way, there was Kosovo and Iraq and a few things like that. And suddenly the Air Force got religion. They realized what they had with a precision weapon delivery system. And since that time, I'm proud to say the Air Force is foursquare behind it and is also defending civil use as part of their charter, which again, I'm very, very proud of what they're doing. Satellites, 72 successes. Purple is Rockwell. I think there was about 38 of those. And then Lockheed Martin, the green for 20, and then Boeing, Rockwell. By that time, Boeing had eaten Rockwell, and there were 12 launches. And now today, most of you, if you're working GPS, are aware that the first couple 3As have been launched, and I think we're heading for about 10 of those. Now, one of the really significant things is right here. The satellites that the United States has produced for GPS are phenomenal in their longevity. And the reason that's important is if you're trying to sustain a constellation of 24 to 30 satellites, and the satellite lifetime is 2 years, that means every 2 years you got to replenish all of them. That's the situation the Russians have found themselves in. They have typically had 3 to 4 year lifetimes. They've had a lot of trouble. I wish them well, and I really do, but they have not been able to stand up even close to what our engineers did. So I'm quite proud of that. There were 2 other events that fostered GPS use. The first occurred when President Reagan announced in September of '83 that GPS would be guaranteed to the world. He did that because the Russians, Soviets at the time, had shot down a Korean Airlines plane over the Kamchatka Peninsula. it was alleged the problem was a navigation error. So Reagan stood up and he said, it's going to be available to everyone. Unfortunately, back then, the Air Force was still wiggling the civil signal a little bit. They called that selective availability. And it's dumb as dirt. The reason it's dumb as dirt is if you have a differential system, you can take it right back out. And the irony was we had the United States Coast Guard broadcasting the corrections to the errors that the United States Air Force was putting into the system. I pointed this out, and the general, a good guy, General Myers, 4-star general, charge of all space, he says, I got you, Brad, but I don't think I can turn it off. Well, President Clinton, we had to go all the way to that level, finally turned it off at midnight on the 1st of May of 2000. And the result for you people that like charts is shown here. This is the wiggles that they were putting in. The scale here is plus or minus 100 meters. And you can see it up and down. And at midnight, it went off. And there's what happened. And the net result is full accuracy to the civilians and also very smooth errors, which meant differential corrections would persist for a much longer period of time. And all in all, it suddenly put civilians on a completely wonderful footing. And that brings me to the subject of accuracy. Where are we, more or less? Here's signal accuracies today. The columns, this is all just horizontal. Vertical, for reasons you probably understand, are about twice that much. Raw GPS at the 95th percentile, something like this, 2.5 meters. If you use differential GPS and use the wide area corrections, you get this, not much better, but you get integrity. You get a message that within 6 seconds tells you if one of the satellites is messed up over the United States. And then real-time kinematic, most of you are aware of this technique perhaps, using carrier phase. Carrier wavelength is 19 centimeters, and I can measure it to 1%. And the result is I can get errors like 2 centimeters, which is great dynamically. It's in a very wide bandwidth. Bandwidth is a wonderful thing if you're trying to control something. And this is in like a 40 hertz bandwidth, which is enough to control, for example, farm tractors. And then geodetic measurements for survey down to a fraction of a millimeter. And this is useful as well for certain applications. So the good news is we're taken for granted. And the applications span all of this. And you're well aware of everything from tracking mooses to the space station to orienteering to fishing, you name it. There are lots of applications. And I'm frequently asked, well, which of these did I foresee? Well, I'd love to tell you I saw them all. Not true, not even close. But I saw some that were immediate. I saw some that were kind of betting on improvements, and or a whole bunch of others I didn't have a clue. And in a matter of fact, in a couple of cases, my students were the ones that went off and built something that showed the world. The value to the United States of these applications has been calibrated about 5 years ago. 5 years ago, just not safety of life or anything like that, just the pure raw economic improvements were over $66 billion a year. So the investment the United States makes of about $2 billion a year in this system is the kind of thing that if someone asked you to get in on an investment like that, you'd instantly say, yes, I think I will. So good news. And so back in '78, just about the time we were launching the first ones, I was asked, well, what will this do? And I drew some these are my hand drawings of applications. And then I got it. This was back when you still had view foils and things. And so this was road grading. I thought we could do road grading. We weren't doing it yet, of course. And this is the one that I should have made my fortune on, automobile navigation. I had a moving map display. I had a head-up display. I had a little voice telling you when the next turn was. anyone ever heard of that? And I had a whole database of emergency numbers and locations you could just punch in. And I thought that was pretty slick, but we didn't do that back then. And as a matter of fact, I briefed this chart to a group of people. I was running a course on managing innovation at Stanford. And it was interesting. There were about 5 people from Japan, and they were furiously taking notes. And the engineers, the automotive engineers from Detroit were sitting there shaking their heads saying, never happened. Well, it turns out Japan finds it useful because their house numbering is not sequential. What does that mean? It means that the next house built gets the next number, I guess. But the point is, this coupled with a database of where those houses are was an instant market. And I'm told that that's the reason that the Japanese were the first ones to really pioneer this application. Okay, I had a bunch more. There's probably another 8 or 10 of these that I drew. Air traffic control, monitoring dams, la-di-da. So how quick did it happen? Well, here is a three-dimensionally controlled bulldozer, 2 GPS antennas. That took about 25 years from when I thought it might happen to when it really did. And then I was very gratified. One of the companies put out this set for 140. Let me show you. You can't read it. Here. I thought this might be it, all the way down to $1,500 each. So I was pessimistic. 149, heads-up display, and something you could just put in your car. Well, I don't mean these charts to simply brag about what we did, but it indicates how far technology has really come. And again, your company and others like you are the ones that are pushing this, and you'll continue, and you'll dazzle me as well. In 1974, we thought we could do aircraft navigation. What we didn't realize, hands off to touchdown, and here was the airplane that did it. The FAA got us to borrow a United 737 with full Cat 3, but we broke in there and just made it by GPS. There are 110 straight landings, and the calibration is between where GPS thought the airplane was and where the laser tracker thought it was. And the scale is 1 meter. Down near the critical end phase, you can see the accuracy is RMS. It's something on the order of a foot or better. We actually think what was happening here is GPS was calibrating the laser, not the other way around, and I still believe that. So Clark Cohen, another name, one of my heroes who was also one of my students, Dr. Clark Cohen. Now, we thought in 74 we could do land navigation, and then in 96, these two, Mike O'Connor and Tom Bell, and another one, Andy Rico, put together farm tractors. And one of the things they did is add this attitude measuring system, and they did it for a reason some of you already understand. GPS measured where the top of the roof was, but you really wanted where the tow bar was, because that, if you're really doing precision work, that's what counts. So there's a lever arm correction that demands your knowledge of the orientation, tilt, etc., of the tractor. How well did it do? Tracking test errors typically under 3 inches. Early on, John Deere kept telling me farmers would never want this. Well, not true. And they've also gotten the message. Now, meanwhile, by the way, I have to acknowledge they sent me, I think, almost $1 million and 2 of these humongous tractors, which leads to some interesting stories, but I'm not going to tell you. At any rate, now it's over $800 million a year farmers are spending on this. Why would they spend that on there? Wow, that's a lot of money. This is why. This is why. Because they don't have to touch the steering wheel, and they can reduce the overlap by 8 to 10%. That doesn't sound like a whole lot. If you were out there fertilizing your lawn, you'd put in a big overlap, right? You wouldn't run it right up to the edge because you might leave some gaps. Well, let's do the math. Fertilizer and chemicals in the United States, this I think is 3 years ago, $38 billion. So the potential saving there is 8 to 10% of that, or north of $3 billion. So again, spending 900 million or 800 million on something that saves them that, the turnaround is 3 or 4 months. And incidentally, that's what farmers believe. They believe when they put the GPS stuff in their tractor, the payoff is 3 or 4 months. Absolutely astonishing. Productivity, again, not something I foresaw, but something that was done. And here's another one. They use these huge trucks. These tires are 10 feet high. And they use them in open pit mines. Very boring work. You go down, someone sticks something in the back of the truck, and the truck goes up out of the copper pit or whatever it is. And enormous savings. And this has been going on for at least 10 years. And uses pseudolights, by the way, for those of you that are fooling with that idea. But watch out for some bad surprises. That's called a bad surprise. The point is, GPS can guide, but don't select the wrong path. And it also gives you some idea of the scale here. So another one that I really like is this, the GNSS watch. I just happen to have one. And it helps you find your way home. And of course, it watches you. And if you aren't moving, it vibrates. And you look on it and it says move. So you got to keep your eye on that deal. What's next? In the next 25 years for GPS and other GNSS, well, Yogi Berra is an old philosopher. He says some pretty nice things. You've got to be very careful if you do not know where you're going, because you might not get there. So let's try to figure out where we're going. PNT is about to explode with opportunities. And if you're following this, you're already aware that we're broadcasting L5 and L2 now. The only real operational signal in the last 15 or 20 years has been L1C on GPS, although there have been some supplements, and certainly GLONASS deserves some credit. But we're about to have 4 new signals at 2 frequencies. GLONASS has gone over to the correct side and is going to deal with CDMA now, 4 signals, 2 frequencies. We've got Galileo about the same. Compass is coming along very, very fast. And of course, the supplements. And the summary is it's going to be, 60 or 70 of these satellites in orbit. And the result, and hopefully with an interchangeable international signal called L1C. And when that happens, you, the user, are going to be the beneficiary of that. But I offer one caution. It is not simply availability and accuracy. There's another parameter that the FAA likes to use, and that's integrity. And the question is the system right now working within spec? And in a lot of cases, you're not all that sensitive. If you're driving a car and you're 100 meters off, okay, you can figure that out. But if you're landing an airplane, it's a different matter. And they have a spec that during landing, there can be no misleading information more often than 1 time in 10 million. And that's a good goal. And it's a good goal for you to think about if you have an application that you're dealing with that uses something equivalent to a landing system. Okay, so I have 3 issues that I'd like to talk about for the future. And these are them. These are they. These are they. I'd like to give you an important challenge for certain users, applications. I'd like to talk about what I think is a large market opportunity, which is quite allied to something I think you're already doing. And then I'm going to talk about what I consider to be a very, very grave threat. And it sounds innocuous. It's not. The challenge. Establishing high integrity control and monitoring of unmanned aerial systems in our airspace. What am I talking about? Well, I'm talking about this problem. If you recall, obviously you all live in California, and if you recall about, 2 months ago, there were some huge fires, and if you picked it up on the paper, 14 firefighter aircraft were grounded because there was a rogue drone in the vicinity. They caught the guy. Someone spotted the drone. And the guy, I don't know if he's going to jail, but he's sure as heck under some rather severe charges. It is absolutely against the law to fly a drone anywhere near a fire without permission from the fire coordinator. And the point is, this joker ended up putting his drone in there and grounding the whole firefighting fleet. And the point is, monitor and control of these kinds of vehicles. We do a lot of them. Here's an application, power line inspection. You can see climbing up one of these towers versus just whipping a drone up there. Wow, what a productivity lever. Some more agricultural inspection, media coverage, security. You can name a lot of things like that. And here's a couple others coming along. Autonomous air taxi. It hasn't really been a market yet, but it's flying. And here's one you might recognize. The point is this air delivery. And if you're going to do that and do it effectively, you have to do it out of line of sight of the operator, in my opinion. And if you do, you've got a monitor and control problem, and you've got to address it. And it has not really been solved yet. There's many applications that fly close to the ground and close to your drones, close to other people's drones, commercial airplanes during takeoff and landing. Every once in a while, you'll read in the paper someone's flying a drone near an airport and they have to stop all operations. Wildfire tankers, I've mentioned, law enforcement helicopters, and of course, general aviation. These are the cowboys of the air, and they fly in a lot of strange places. How do you coordinate what they're doing with the drones? Part of a solution might be something like this. This is a GNSS-based geofence system. This little chip goes on a truck, and the fleet operator says, I don't want you going in these red areas on this map. He can adjust those rather rapidly, and he can also have it reported to him when that truck penetrates these areas. And I'm suggesting that there ought to be a three-dimensional way to do that, and do it as exclusion or enforcement, your choice. I don't know exactly what engineering is going to work on this, but I suspect that GNSS is a key enabler for whatever we're doing. Here's my idea of sky tunnels. It's not all that original. Little macaroni tubes, and you're authorized, you get permission and are authorized to fly in the middle of this macaroni tube. And here's a different macaroni tube, and these two do not intersect. So that's an application that works. And to ensure no collisions. How big is the problem? Well, by 2022, FAA says there's going to be close to 3 million drones. That is one heck of a problem. And they are rapidly trying to evolve safety and security concerns, legislation and rules. They, I think in the last month, they came out with a new set of rules on what the monitoring has to be. And I would urge those of you that are in this business to follow that very, very closely and help them find an answer. Help them find an answer that meets your market, meets your profit goals, and at the same time preserves safety for the United States airspace. I don't think there's going to be any simple answers. This is going to be a hard one. And the drone operators are pleading to be allowed to fly beyond visual line of sight. And how would they do that? Well, I think they need GNSS. But how are they going to do that without having some kind of an authorization and certification system in place? And I've mentioned geofencing and the possibility we could extend that to sky tunnels. The opportunity that I'd like to talk about. Delivery in 2 dimensions, not 3. And I'm talking unmanned cargo vehicles on US long-haul freeways. I'm going to give you a rationale for why I'm talking about this. Another way to look at it, autonomous 18-wheelers is what we're talking about here. And of course, driverless cars have already been demonstrated. This happened, 15 years ago at least. I noticed Google's on the side of the Stanford car there. I thought that was nice. And As I understand it, Google is also working on something called Waymo, and they've had a demonstration going on in Arizona for some time. But of course, you still have a safety driver in it, very prudent. And in part, the problem is even if statistically this is safer, the media will pick up on each and every accident and blow it out of shape. And it will be very, very hard to establish that market in a way that you don't have a problem. So it's going to come, but I don't know exactly when it's going to come. And I hope it's sooner. So we're talking about the payoffs of doing 18-wheelers. And I focus on 18-wheelers because if they're fully autonomous, they are not hauling people around. Drivers, up to almost 100 grand a year, and they can only go for 12 hours. If you make them autonomous, those trucks could go for close to 24. 3 million full-time drivers. I'm told that truck driving is the largest job category in the United States. And then I got to thinking about it, and everything from post office to 18-wheelers. And they predict a shortage of about 250,000 drivers this year. And if you drive down I-5, every truck almost has an advertisement. We give great benefits. Call us. And of course, platooning saves fuel in the economic area. In safety, the latest data I had was 2012. Trucks were involved in 1/3 accidents, 4,000 people killed, mostly in the cars because mass being what it was, they don't win the battle. And 90% were driver error. Safety features are already being installed. You probably own a car with some of these, and I see that simply evolving. And this is a statement Wired Magazine made: let the trucks drive themselves, and you can improve safety, meet increased demand, and save time and fuel. So the technology are things that I know you are working on right now. High precision vector, GNSS, real-time kinematic MEMS, radars, sonars, LiDARs, digital cameras, and of course, that's all wrapped together in software, artificial intelligence of some kind, if you want to call it that. But at any rate, you're going to need that. What are some examples? Where are we in this? I think that general acceptance and certification without human cargo is going to be a lot easier than when you put people in it. But that's just me. And I am not trying to discourage you from working on those elements that use or have human cargo, but I think that something like this is going to happen sooner. Well, where are we? Here's an autonomous truck that was demonstrated, I think this year, 2,800 miles from California to Pennsylvania in under 3 days. Winding roads, went through construction, in a realistic environment, but of course they had a safety driver. Here's some convoy operations, or platooning as they call it, not yet fully automatic. They claim they realized 10% less fuel because of decreased drag. To me, that sounds like it would be reasonable. Here's another example. It's actually earlier. This is a car autopilot convoy, and if you look carefully, each driver has their 2 hands out the window, and down the freeway they go. Don't try this at home. So the issues that are going to have to be resolved are at least this list. And again, I come back to integrity. The fact that the system isn't lying somehow. And that was the big issue when we got WASP certified finally. So again, this 10 to the -7 that FAA uses for that, it's certainly going to use GNSS to help it, but the FAA spec is equivalent to no more than 3 seconds of bad data in a year. Let me get to my third subject, spectrum interference. And if any of you go to the Stanford annual conference, you will know I talk about this a lot. Spectrum interference. And I've got my hat on now. I am a co-chair of the advisory board to the federal government. This is the PNT Executive Committee. 9 departments in the government represented is a powerful committee, represented at the number 2 level. The Deputy Secretary of Transportation, the Deputy Secretary of Defense are the people that chair this operation. So the advisory board reports directly to them, and it is an independent advisory board. We take as our mission that we are a major defender of current and future PNT techniques and applications. So here's the issue. You could look at interference as being illegal jamming, such as this handheld jammer, but what I am more concerned about is licensed intrusion. I'm going to give you a few charts explaining that. I'm not going to give you all the data because we would be here a long time. Here is GPS 1575, our main frequency. Here are 2 adjacent bands which are currently licensed to a company called Legato, but they're only licensed to broadcast from space. So by the time it gets down here, GPS could care less. We know how to handle that. But they want to change what they're doing here to ground transmitters. And initially, they said they wanted to go to 15,000 watts. 15,000 watts would saturate the front end of a GPS receiver with that close a frequency. It's not a matter of filtering, you're just overpowering it. And as a matter of fact, what they had asked for was 5 billion times GPS power at a range of 200 meters to their towers, and they wanted to have 80,000 towers. They have apparently taken this upper band off their request, but they are still requesting that this lower band be relicensed. And the problem is fundamentally, and they've dropped the power to 10 watts, and the spacing has not been specified, but it was 400 meters before. They claim that they're going to do 5G, and if you look at the 5G discussions, 100 to 200 meters is about what they'd be using at those power levels. And of course, the problem is it's too close in geography and it's too close in frequency. Why do I say that? Before I do, what would be affected? Here, the most affected are the high-performance receivers that have wide band front ends. Here's some survey receivers in an urban area. Here's our old friend, the tractor, the bulldozer with GPS on it. All of those are apt to be within that distance. The high productivity represents over half of the $60 billion per year I was telling you about. So this is half of the productivity benefits we calibrated. Not a good deal. And by the way, what about the issue we just talked about, RPVs and unmanned aerial systems? Again, are they going to be within 400 meters of these transmitters? And if so, what happens? So let's talk about what might happen. DOT, Department of Transportation, ran a series of extensive tests defining where a GPS high-performance receiver would start to get degraded. And they did that on the basis of if you raise the noise floor more than 25%, you're starting to degrade the timing accuracy. You can still lock onto the signal, but the timing accuracy starts to go. They call it the 1 dB criteria. It's internationally accepted. So put your mind around this little red circle. Within it, you have increased the noise floor too much. Outside, well, you maybe have increased it a little, but GPS will tolerate that. So define that as the circle and then say, well, within that radius, I don't want to have that happen. How much of an area can you degrade? So after getting a lot of pushback from my board, I said, well, I think we ought to tolerate 10%. So we put down 10%. Obviously, if it's not going to work, you could either reduce the power in that degrading transmitter or you could increase the spacing. Well, let's quantify it. What do we have to do? First of all, if you're only going to degrade 10%, it turns out geometrically This spacing is about 6 times that radius. And you can go in and work out very simple geometry problem and how that comes about. So keep that in mind. Those are the little cookie cutters that are around. And the question is, what's the spacing have to be if it's 10 watts? Well, they quantified that. They looked at I think they tested 43 different high performance receivers. So here is a logarithmic scale, factor of 10 between each microwatt to 100 watts. And here is the spacing, 10 to a kilometer to 1,000 meters. And what the DOT tests showed was if you're in this red area, you're going to increase the noise floor more than you should for high performance receivers. If you're in the white area, you're all right. Where is Legato? There they are. They are a factor of 10,000 away from the white area. So the point is, their power is not close. It isn't like you're arguing over a factor of 10. You're arguing over a factor of 10,000. The other alternative is to take the 10-watt receiver, a 10-watt transmitter. Here's Legato operation right here. 10 watts at about 100 to 200 meters. Take it and slide it this way, i.e. further out in range until it gets over into the white area. That's the other alternative if you insist on 10 watts. What would that be? Well, we ran those numbers and it's the square root of 10,000 because it falls off as 1 over r squared. So a 10-watt transmitter spacing has to exceed 20 kilometers, far greater than the 200 meters. So the caution I would give you, Alphabet, this may affect you. And I would suggest if you look into this and feel strongly about it, you should get someone in your corporation to file a letter with the FCC and tell them you don't think this is a good idea. Well, I'm about done. Why has GPS, let's finish on a positive note. Why has GPS become ubiquitous? Signals free, reliable, available, accurate, guaranteed. The receiver cost is no longer a driver for almost any application you can think of. The innovation in your company and many others has flourished way beyond our original vision. And the applications generally help with safety, help with productivity, or they're convenient, or they're fun. My GNSS watch said my time is up. And the revolution continues. Thank you. Is there any time for questions? No. Thank you.
I don't think you said anything about spoofing of GPS and how we might authenticate GPS in the future to guarantee that we're listening to the right satellites.
Yeah, spoofing is one of the current problems that people are agonizing over. I contend that the problem is not really spoofing in a smart receiver. There are so many ways to fix that. For example, there's a lot of complaints about maritime shipping in the Black Sea because the Russians evidently keep spoofing them and telling them they are in Moscow instead of in the Black Sea. Well, if they had 2 antennas, they would never be spoofed. They might be denied. But as soon as you have 2 antennas, they're both giving the same answer. And I use those 2 antennas generally for azimuth of the ship. But most of those ship drivers are so cheap. They would not put something like that in there, and they're going to have to come around. One of my friends, John Betts, is famous of calling the receivers that are spoofed ignorant receivers. There are ways also to put in authentication into the signal itself, and I think that's being studied. I think it might be a worthwhile thing to do. But by and large, there are so many checks that you could use, particularly at the carrier level, that the signal you receive is erroneous. My favorite is that we go to cheap beam steering antennas. And if you use a beam steering antenna, if that signal is coming from the horizon, you know it's not a real satellite, especially if all the signals are coming from the same place. So, good question. Thank you.
I have a follow-up question.
Yes,
You
please.
mentioned solutions with multiple antennas and beam steering antennas.
Mhm.
What if you're space limited? What if you are trying to build a very small receiver and you can't put multiple antennas?
Well, look, if an enemy puts in a strong spoofing signal, it's equivalent to a jammer for you. Now, if it is not that strong, if it is at some threshold, you can use RAIM, you can use listening to every satellite in view and casting those signals out. Now, whether he can give you a plausible signal is sort of a two-player differential game. But the bad news is if you have a very simple receiver and he puts in a powerful spoofing signal, he's equivalently jamming you, not spoofing you. At least that's my view.
All right, thank you.
You're welcome.
I wanted just to know if you had thoughts about user privacy around their locations.
I was pleased about 5-10 years ago, the Supreme Court said you can't track people. They're talking to the law enforcement. You can't track people without a warrant. And I really, really agree with that decision. It's obvious that you can capriciously track people today. One of the persons, if you're a father or a mother, that you would want to track are your child, but that's cooperative. That isn't any hostile intent. But I believe in warrants as a technique to ensure some degree of privacy. GPS opens up a lot of cans of worms with their ability to locate people. And, angry husbands and wives can track their husbands and wives, or wives and husbands, using a device they attach to their car, I guess. I don't know how to stop that.
While I have you, when you and your team put in the initial sort of design and around the timing and starting the week number in 1980, did you expect that the 10-bit week number rollover would actually impact the system, or did you think there's no way those original satellites will still be there by then?
Yeah, of course, the issue isn't just the satellites. The issue is what you do in the user receiver, and any change in that signal structure, as you know, is a big deal. Candidly, we were so constrained, 50 bits per second, all the ephemeris. See, now we have cell phones, so I can get the ephemeris directly from the cell phone company. I don't have to sit around, but 50 bits per second, and we got enough so that you know where the satellites are, not just your satellite, but all of them. I thought it was magic, and that Mel Birnbaum, that guy that I showed you, he was the guy that figured out how to do that. And so the crisp answer is no, we did not think that far ahead. Thank you very much.
Thank you.